So I think today's class might be a little bit short, but I often think that it never ends up being that way. I always talk slower than I think I'm going to talk. But today what I want to do is talk about the compositional formula for exponential generating functions. Okay. And just to remind you where we are, we're talking about exponential generating functions as a way to count combinatorial structures that have labels on them. And then we have been defining these operations of combinatorial structures that correspond to algebraic operations on the exponential generating functions. So we know what adding exponential generating functions corresponds to. We saw what the product corresponds to. We saw what exponentiation corresponds to. We saw what the logarithm corresponds to. But what we haven't seen is what composition corresponds to. So that's what I want to do today. So if B and C are some labeled combinatorial classes, then I'm going to define their composition to be sum k equals 0 to infinity bk product with set k of c. Okay. And actually, I'm going to need to have no. So just like we did with exponentiation, I don't want to have things of size 0 in my set B. So actually, that's what I wrote here, but I don't think that's what I mean. I think what I mean is C. Just like when we wanted to do the exponential of C, we wanted to have no objects of size C. Here we're doing, actually we did one example of this, which is when B is exponential. So then we did, B is e to the x. Then we did this operation. And in that case, we demanded to have nothing of size 0 here, and we're going to do the same here. Okay. So let's think of what this is. So what this does is that you're going to take your so to get a structure on a set S, what we're going to do is the following. So for some value of k, we're going to take our set S and partition it into k pieces. Okay. So partition S into sets S1, S2, up to Sk. Okay, this is what this is doing. Well, this is what this is doing, but now we're going to put a C structure on each one of those sets. So put a C structure on each set Si. Okay. So if I were to stop here, I would just be describing this, right? As I range over the different values of k. But now I want to put a B structure on this set of k elements. Or to B structure on the blocks Um, the setup blocks. Okay. And so, well, you can probably imagine what the theorem is. And we'll do a couple of examples of this in a second. But the theorem is that this corresponds to composition of exponential generating functions. So the exponential generating function of this new combinatorial class is the composition of those of B and C. Okay. And the proof is going to be pretty simple, so let's do it. So what is B of C of Z? Well, let's say that let B of Z be the sum of bk z to the k actually, I don't even need to give names to these coefficients. So if I do this, then I'm going to get sum from k equals 0 to infinity of, well, b of something is bko, and this is like an exponential generating function. So b of z is the exponential generating function for the sequence bk. Bk is the number of objects on a set of size k. So then I get bk c of z to the k over k factorial. Okay. And by the way, let me remind you that this is where I run into problems. If I were to have things of size 0 here, then this c of z would have a constant coefficient, which would be the number of things of size 0. So this would always start constant plus other things. When I raise it to the k, I'm always going to get a constant, and so that means that the constant coefficient of this would have infinitely many terms. So that's why I need to demand this condition. Okay, and actually this is basically it, because this was exactly the generating function for set k of C. We prove this. You can look it up in your formulas. It's pretty straightforward. And that's it. So the proof of this is pretty easy. The point is how you use it. So let's do a few examples of this. So for example, let's consider ordered set partitions. So what's an ordered set partition? It's a way of writing a set N. A set is joint union of k sets, and these sets are ordered. Okay? So I care about who is S1, who is S2, etc. These guys are ordered. Okay. So, and sometimes we write this as, for example, a set partition of 1 up to 7 would be like this one: 3, 4, then 2, 5, 6, and 1, 7. And so, but again, it's important who goes where. So if I switch 1, 7, and 3, 4, that's going to be a different ordered set partition. Okay. So you might say, okay, well, we basically already did this because we already counted set partitions. And we did, right? So how many ordered set partitions were there if I don't care? Sorry, how many set partitions were there if I don't care about the order of the parts? So you can answer that in two ways. So one answer would be that this is given by the Stirling numbers. Right? So remember that the Stirling number of the second kind, S of nk, counted precisely the number of these kinds of partitions where I didn't care about the order of the parts. And then an ordered set partition, well, it's just k factorial times S of nk. Right? Choose the partition and then order it. So for a fixed value of n and k, we know how to do this. But what if I vary k? If I vary k, and if I didn't care about the order, then those were the Bell numbers. We talked about those also. But now, actually, we don't know about the total number of ordered set partitions. And we can't get it so easily. I mean, it's not just some factor of the Bell numbers, right? It's a different question. So how do we do this? Well, it's actually perfectly suited for what we're doing here. Because what is an ordered set partition? So this is going to be my name for the combinatorial class. Well, what I'm doing is that I'm partitioning my set S into classes, right? Sorry, partitioning my set S into some subsets as a partition. Now here they're not ordered, right? And so what I need to do is that I need to put an order on those classes, so I need to put a permutation on them. And so this is precisely the composition of permutations with this, where here I'm putting a trivial structure. So this is going to be the composition of permutations and just sets of size greater than or equal to 1. So again, let me say this again a little bit more slowly. So remember, what is this combinatorial class set greater than or equal to 1? It's a very simple thing. Just for every set of size greater than or equal to 1, there's one object in that combinatorial class, which is the set itself. I don't do anything to it. Okay? But if the set happens to have size 0, then I delete it. Okay? And so if I apply now this to here, I'm saying, okay, to get a structure of this kind, what I'm doing is I'm partitioning my set S into S1 up to Sk, right? Then I'm putting a C structure on each set Si. But putting a C structure is not doing anything unless the set is size 0, in which case you delete it. Okay. So in other words, what I'm doing is ensuring that I don't have empty parts in my partition. And then I'm putting a perm structure on the blocks. So I'm just choosing a permutation in which to list. So it's just that. And so given that, then that means that I know how to compute the generating function for these numbers. I don't know, let's call them maybe ordered partitions of n, z to the n over n factorial. This is the composition of permutations and sets. Okay? And now we have to remember, what was the generating function for permutations? So remember that these are exponential generating functions. So if I want permutations, then there's n factorial permutations of size n, so I get 1 over 1 minus z. So this is 1 over 1 minus z. And what was set greater than or equal to 1? I just have one set of each size, but for n greater than or equal to 1. Okay. And so this is e to the z minus 1. And so I take this and I evaluate it at this. 1 over 1 minus, and then I take this thing. This thing is e to the z minus 1. So this is equal to 1 over 2 minus e to the z. Okay. That's the number of ordered set partitions. I know some of you in this room have thought very hard about the permutahedron or the braid arrangement. And what we just did is that we just counted the faces of the permutahedron or the braid arrangement. If that means something to you, great. If not, then it's a good reason to learn about these things. But yeah, so order set partitions, okay? Very easy to count using these techniques. Okay, now what if I want to count this a little bit in a little bit of a finer way by counting not only the number of order set partitions of n, but let's count them by their number of parts. Okay. So I want to count them by number of parts. So what I want to do is order partitions of n into k parts. Okay, and actually we just talked about what this is, right? This is choosing a partition of n into k parts and then ordering those parts. If the number of parts is fixed, then I can do this. So what if I want to write down the generating function for these things? It's a double generating function because I have two parameters. And I'm going to use z for n as before. We're going to use y for the number of parts. And again, it takes some practice to know whether you should make it exponential or not. And I'm going to show you that in this case, you get a very nice formula if I make it exponential in z and ordinary in y. So let me rewrite this a little bit further. Let me rewrite this as z to the 1 over 1 factorial plus z to the 2 over 2 factorial, etc. Okay. So this is what we did here. Now, I kind of want to make the same computation, except that I want to give weights to my order set partitions. I want a particular order set partition to get a weight of y to the number of parts. So what I want to do is that I want to imitate this. But I'm going to change it a little bit. Because what I want to do, and again, let me maybe I'll put this in red to know that this is some kind of weight that I want to assign to each partition. Okay. What happens that one way of thinking about what's going on here is that you're making an ordered set partition by choosing parts of size 1, parts of size 2, parts of size 3, etc. Right? And remember, when we have 1 over 1 minus something, we're making a sequence. Right? And we're just making a sequence of some set, then some other set, then some other set, and this and that set is going to have size 1 or size 2 or size 3, or so on. Okay? And every time that I choose one of those sets, I want to give it a weight of y to say I choose a new part. And so what I want to do is put a y here, a y here, a y here, and so on. Okay? So every time you choose a new part, you give it a factor of y to signify that part, and then when you carry out this computation, each partition is going to come out with the right weight, which is y to the number of parts. Okay? And so this is basically going to be my formula, and then this is pretty easy to compute from here on, because this is 1 over, you see this is 1 minus, I just put a factor of y, right? I mean, if I put a y, if I put a plus y, and then I put a minus y, then I'm going to get minus y times e to the z exactly. And maybe to color code it to make it a little bit clearer, so that this y is the same as this y, and then this is the same as this e to the z. But this e to the z is missing the first term, which is why I need to correct for it here. And so then that's my two-variable exponential generating function for ordered set partitions. Okay. Any questions about it? Yeah.
I guess I'm curious, if we already knew what the coefficient was, what more do we get out of having the generating function?
I mean, this is okay. So let me first tell you that the reason that I wanted to show you this is that now I want to show you something based on this, which is harder. Okay. But even then, okay, the question is, what do I get new from this? Well, you know, you get a new generating function for Stirling numbers, I guess. It's in two variables, and it's kind of exponential in z, and it's kind of the opposite of exponential in y. You see, it comes with terms k factorial y to the k. So it's some kind of new formula for Stirling numbers that, I don't know, depending on what you might try to do with Stirling numbers, it might be that this is the formula you want. But yeah, I mean, it's just some formula. I want to show you a more interesting example of this computation. Yeah?
Can you just quickly explain again why you only put powers of 1 for y?
Oh, so the question is, why did I only put powers of 1 here for y? And the reason is that I was explaining that each time an ordered partition is like making a sequence of sets, a sequence of subsets that add up to your total set. And those sets are being chosen whenever by these blue things. So here I'm saying choose a part of size 1, choose a part of size 2, choose a part of size 3, and so on. But no matter what the size of the part is, it's only one part. And the red exponent would be the number of parts. And so that's why I put one part every time that I have a part, no matter what size it is.
I thought that wasn't the 1 and the 2 counting the size of the entire set?
This 1, this 2, this 3, they count the sizes of the individual parts of the partition. And then each y set gives you a +1 whenever you have a new part of the partition. And therefore, this is going to be the number of parts of the partition, and this is going to be the length of the total size of the set. One way of saying this might be that, you know, to write this. So I have this thing. But I guess one reason that I wanted to show you this is that sometimes you're interested not only in counting objects, but in counting them with a weight. Like in this case, my weight is y to the number of parts. And the point that I want to make is that often you can just feed this into here by considering these kind of weighted combinatorial classes. And so I might call these like, I don't know, like y-ordered set partitions, the ones that come with this weight. And the weights of the partitions are inherited from the weights of the sets. Okay? Each set has a weight of y to the 1, and then these weights multiply to give you the weights of the ordered set partition. Okay? So this is kind of a symbolic way of saying what I just wrote here. I don't know, some people prefer this, some people prefer this, but I'm kind of saying the same thing here. So let me show you another example of this. Actually, maybe one exercise that I won't carry out, but that is carried out in the book so that you can test your understanding of this, is to find the number of ways if you have n people, first putting them into lines, and then putting the lines around a circle. Okay, so like this might be an example. Maybe you put them into, let's say, 3 lines or 4 lines. Okay, and then you put the 4 lines around a circle. So maybe this is person 1 and person 3, and this is person 7 and person 2. 9. This is person 4 and 5. This is person 8, followed by person 6. Did I miss anybody? Let's say person 10 also. Okay. So is the question clear? You take n people, you split them into some number of lines, it doesn't matter what number, and then and each line has a front, right? And then you put those lines around a circle where the person on the circle is the person in the front of the line. Okay? So find the number of ways of doing this. This is a good example of a problem of this kind. So you should try it out, carry it through, and find the formula, and then compare it with Stanley's book.
So in this case, we have fixed 4 lines, and each line has at least 1 person.
That's right. That's right. Each line should have at least 1 person, and the number of lines is not fixed actually. The number of lines could be anything. It's the number of people that is fixed.
K in this case is not 4. K ranges for each line.
I won't say what n and k is. I'll just say this is the question that you want to solve, and part of the answer will be to figure out what's n and what's k and etc. Okay, so let me give you another example of this. And this example comes from homework 2. So f of nk is going to be the number of sequences of sets S0, S1, up to Sn. They start with the empty set, they end with the empty set. These are all subsets of the numbers from 1 up to k. Okay. Such that for each I, either Si is obtained from Si minus 1 by adding one new element, or by subtracting one. Okay. And there was some formula that I asked you to prove for this. And I think the first thing to ask is, where did that formula come from, right? I mean, once you know the answer, it's easier to prove it. But so what I want to show is that the formula just comes out of this technique. We kind of frame it in the right way. So let's start by doing this in an example. Okay. So let's say that we start with the empty set, then add 1, then we add 2, 1, empty, 3, 1, 3, 1, 3, 5, 3, 5, 5, 2, 5, 2, empty. Okay, so this is an example of such a sequence. Each time you either add one new element or delete one new element, start with the empty set, you end with the empty set. So in this case, what's n and what's k? Well, n is the number of, so I start S0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 sets. And what's k? K is the, these are subsets of the numbers from 1 up to k. So k should be at least 5. Let's say that k is 5. And so this is one of these sequences. Okay, well, the first step is going to be to rephrase this. So let me, at each step, just say, who did I add or who did I subtract? Okay. So you see here, I added 1, I added 2, I subtracted 2, I subtracted 1, I added 3, I added 1, I added 5, I subtracted 1, I subtracted 3, I subtracted 2, I subtracted 5, and I subtracted, sorry, I added 2, subtracted 5, subtracted 2. Okay? Is this bijective? Well, it is, right? Because you start and you say, okay, well, I know I'm supposed to start with the empty set, then I have to add 1, then the question is that at each point, do you add it or do you subtract it? Well, it just depends. Do you have it or do you not have it, right? So I have to add 1, then I have to add 2, then I can't add 2 because it's in there, so I have to delete it. So at each step, you add it if it's not there, or you delete it if it is there. So this is bijective. Okay? Now, another equivalent way of writing this is just to say, where are the 1s, where are the 2s, where are the 3s, where are the 4s, where are the 5s. So where are the 1s? The 1s are in positions 1, 4, 6, and 8. Right? Then where are the 2s? The 2s are in positions 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12. Where are the 3s? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. Where are the 4s? There's no 4s. Where are the 5s? 1, 2, 3, 4, 5, 6, 7, 11. Okay? And again, it's clear that this correspondence from here to here is bijective. Now, the question though is, okay, what did I get in the end? Well, this is clearly an ordered set partition, right? Is it? Well, it's almost an ordered set partition, except that in set partitions we're not allowed empty parts, and here we are allowing it, so this is actually a weak ordered set partition. Okay? Now it's a weak ordered set partition of what set? Of n, right? Where does the k come in? Okay, is the number of parts, right? Okay. Now, does every weak order set partition of n into k parts give me a solution to this problem? So the question is, let's try to reverse this, right? So if I give you a weak order set partition of n into k parts, is it going to correspond to a solution to my original problem? So it just depends. So you just have to make sure that at the end you get the empty set, right? It's clear that you can start, from here you can get to here, from here you can get to here, starting with the empty set. But the question is, will you end at the empty set? How do I know if I end at the empty set or not? Well, I just need to make sure that every element is not in the set. And you see here, I added one, deleted one, added one, deleted one. Because there's an even number of ones. Oh, there's an even number here. One ends up not being in the set, right? And that's true for each part, right? Like here I add 2, delete 2, add 2, delete 2, add 3, delete 3, add 5, delete 5. And so if I want to make sure that everybody's deleted by the end, then I need to make sure that these parts all have even size. And that's all that I need. So into k parts of even size. Okay. And that's exactly what I'm trying to count. And if I say it like that, then it sounds more believable that it belongs in today's class. Okay. So how do I do this? Let's try to imitate what I did here. So, and I don't want to delete this because I want to kind of imitate it. So, okay, let me call this combinatorial class this. Okay, this is this. So what is this combinatorial class? It's very similar to this one, right? It's a permutation of what? It's a permutation of sets, but what restriction do I have on my sets? Those sets have to have even size. So this is going to be the combinatorial class that does nothing to the sets of even size and throws out the ones of odd size. Should I also be doing this thing of greater than or equal to 1 here? Remember that I wanted to make sure that C didn't have things of weight 0. So what do? It's a bit of a problem because actually I want to allow things of part 0, parts of size 0. Now, the thing is that I don't just want to do this for a fixed value of n, I want to do it for n and k. Okay? So I want to introduce weights. And I do it in the same way as before. Okay? And you see, the thing is that now I get lucky that this problem is magically fixed, because now the empty set, the weight of it is y. It's not a constant. Okay? Which means that this actually is going to make sense. It's fine. Okay? So then, what do I get? What I get is that the sum over n and k of my problem, f of n k, y to the k, z to the n over n factorial, is equal to 1 over 1 minus what? Well, it's kind of a similar thing. Except that here I was allowed every part, I was allowed sets of size greater than or equal to 1, which is why I had these guys. Now I'm allowed sets of even size. Okay? So I'm allowed a set of size 2, set of size 4, etc. And I'm also allowed a set of size 1. Okay, but I need to put my y weights in, and let me keep them in. Somebody have a question or comment?
You said size 1, and you mean 0?
Size 0, sorry. Yeah, so I'm allowed blocks of size 0. And now let me put my weights in. Right, so I get a y here, and a y here, and a y here, and so on. Okay. And so this is equal to 1 over 1 minus y times something that I should remember. I should remind myself, how do I compute this thing? So what is 1 plus z squared over 2 factorial plus z to the 4th over 4 factorial, etc. Does anybody remember what that series is?
Me only because I didn't know. I should have known. What is it, cosine?
So this is hyperbolic cosine. It's one of these functions that you never see. And one way of seeing it is that this is the same as doing this one. Right, that's e to the z. Now add the one with alternating signs. What's that one? That's e to the minus z, right? And so when you add these, what you're going to get is 2 1s, 2 z squared, 2 z to the 4th. So you're going to get twice that. So I should take this and divide it by 2. So I get e to the z plus e to the minus z over 2, which is this cosh, hyperbolic cosine of z. But you never thought you were going to see that in a combinatorics class, but there it is. So that's it. This is the generating function for our problem. Okay? And in a sense, it couldn't be, well, it couldn't be much shorter. I wouldn't necessarily say that it's really easy, but it is pretty short and compact answer. Okay? And that's fine, but we want more because we actually want the formula. I mean, this means you can feed it into any computer algebra system and you're going to get a bunch of numbers, but let's see if we can exploit this to get a formula. So we get 1 over 1 minus y times e to the z plus e to the minus z over 2. Right? Let me expand this as a geometric series. And let me try to use the same letters that I used here. So let me expand k greater than or equal to 0, y to the k, e to the z. By the way, can you see why I chose the letter k here? I could choose any letter to do the summation. But the reason that I chose k is that this y to the k is the same as this y to the k. Right? And then this is all a function of z. So that's why I chose k. So it looks like I'm partway there. Now, how do I compute this thing? Well, that's a binomial theorem, right? Sum over k greater than or equal to 0. Let's get that 2 out of the way. Okay? And then we'll use the binomial theorem, something plus something to the k. So that's equal to a sum from I equals 0 to k of k choose I, the first thing to the k minus I, and the second thing to the I. Right? Okay. So let's continue. Y to the k, 1 over to the k, sum, I equals 0 to k. K choose I, actually this is easy. This is just e to the z times k minus 2i. Okay. Now, let me take that thing and find the power series. And this is just an exponential, right? And so we know that this is going to be the sum over n greater than or equal to 0 of k minus 2i to the n over and 0 to the n. Right? Okay, this is a little bit messy, but you see, we were looking for the coefficient of this thing. That's our number, f of nk. And we have y to the k, z to the n over a third. So that means that we found our coefficient, f of nk is equal to, well, you see this is not a triple summation anymore because we're doing this for a fixed k, for a fixed n. And we get sum from I equals 0 to k, or whatever I didn't square, right? K choose I, k minus 2i to the n, and then over k. Which should remind you, this is what the formula looked like, and it was very puzzling. It had negative terms, and you couldn't understand why it had negative terms. So now you see one place where it comes from, naturally. It just kind of falls out like this. And then, okay, it's a formula, and then we need to deal with its complications, but that's the best available formula for this problem. Okay. And I think this will show you, whenever in combinatorics, you see problems where the answer is some summation, and sometimes it's not the prettiest summation. Usually the reason is that it comes from a computation like this. In this case, it didn't turn out so ugly, but sometimes you see problems where the answer is a triple summation, and when you see that, it's probably because it came out of a computation like this. Okay. So that's the compositional formula for exponential generating functions, and how it plays out in some examples. And I mentioned that if you took my class in hot algebras, we talked about the Faadi-Bruno formula. And the Faadi-Bruno formula is exactly this, which might surprise you at this point, but you know, we did this in a different language, but it's the same thing, and there are half algebras hiding behind here that we could uncover one day, or you could uncover it by watching the videos of that class. Okay. So let's talk about. Okay, so now we did addition of exponential generating functions, multiplication, exponentials, logarithms, composition. What's next? What else do you do in analysis that we haven't done here? Calculus, right? Derivatives. What do derivatives mean combinatorially? If f of x is the exponential generating function for some kind of combinatorial object, I don't know, let's say f structures on n, then the derivative, oh, z is what I've been using, right? The derivative is the exponential generating function for f structures where you just kind of put in a ghost element, a new element. It's a little bit strange, but taking a derivative to the power series is like making your set 1 bigger. Again, the proof, all of these proofs are pretty easy. So what's f prime of z? Well, we just take f of z, which is this thing. Let's say f of n, z to the n over n factorial. Right? This is f. F of n is the number of f structures on n. And we take the derivative. Okay. And remember that for us, the derivative is just the kind of we're not really thinking of a limit here. We're just formally taking every z to the n and doing the derivative of z to the n, right? Which is n z to the n minus 1, so you end up with this thing. And this is the same thing. Oh, but now the term n equals 0 disappears, right? You never get z to the minus 1 here. Mm-hmm. So you only get this for n greater than or equal to 1. The constant term just disappears when you take the derivative. And now let's just reindex so that this is n. Now n is greater than or equal to 0, but you see now I need to put f of n plus 1. So this is the number of f structures on n plus 1. That's just what it is. So it's a simple thing, and it has nice consequences. And again, I'm going to do first an example that we know very well, and then an example that we haven't seen yet. So, permutations. Okay. So what do I get when I apply this to permutations? So let's say, I don't know, n is equal to 8. Okay. So if I want an element of the derivative combinatorial class, then I should take a permutation of the numbers from 1 up to 9. So I don't know, let's say it's 1, 3, 7294685. Okay. Now, the thing is that it's a strange thing to think of this as being a combinatorial structure on the set from 1 up to 8, because it's not on the set from 1 up to 8, right? We have this extra element that's in the way. So how can we get rid of that element and think of this really as an honest structure on 1 up to 8? Well, nothing that we can do is just throw it out. What do we get? We get this. Okay, but I want it to be the same structure. Can I recover this permutation from this? Well, not if I regard it as a permutation from 1 up to 8, but yes if I regard it as a pair of permutations, this one, comma, this one. Some permutation of some numbers, and then some permutation of the other numbers. And then, if I want to put the 9 in, I know that I need to put it in the middle of the two parts. Okay. So what I'm saying is that a permutation of a set 1 bigger than you is the same as taking your set, splitting it into two parts, and doing a permutation of each part in order. Yeah?
What if the 9 was in front?
If the 9 was in front, then this would be empty. It's okay. So it will be the permutation of the empty set. There's only one, which is the empty permutation. What do we call this combinatorial class? This is something, and what we're doing is we're taking the set, we're splitting it into two parts, putting a perm structure here and a perm structure here. This is exactly product. Right? This is exactly an element of perm star perm. And so you see what I'm saying is that taking the derivative combinatorial class is the same thing as taking the square. Perm, I don't know, wait. If we call this like perm prime, then this is going to be the same as perm star perm as combinatorial classes. So then what does it mean? It means that we can now take this to the level of generating functions. So, the ordinary generating function for permutations, say it's P of z, satisfies the following differential equation. The derivative is equal to the square.
Do you mean exponential?
Oh yeah, exponential. Thank you. Let me test your understanding of what's going on. Should I divide by 2 or should I leave it as P of z squared? And why?
I mean, divide.
I say leave
You say leave it. We had formulas where we had P of z to the k over k factorial.
If you divide by 2, wouldn't that switch the order of those two, and that would give the same permutation back? That doesn't work.
So that's the thing. When you take one of these things and you raise it to the k, it's like taking a k-fold product. If I were to divide by 2 factorial, I would do that if this was the same as this. Right? If these guys were not ordered. But when I have a left and a right, then I just multiply them, and it is just perm star perm. If I had P of c squared over 2, that would be like doing set 2 of the thing. I'm not trying to confuse you. I'm just making sure that we know what we're doing here. Okay, so I have a differential equation. What do you do to a differential equation? Solve it, right? But can we solve it? Well, what do we need for a differential equation to solve it? I mean, this one is pretty easy. It's a first order differential equation, but we need more information if we want to solve it. You need some initial data, otherwise you can't solve the differential equation. The initial data might be, for example, saying what is the value at 0. So what is the value at 0? So this is exactly what Cervantes just talked about. The value at 0 is the number of permutations of size 0, which is 1, the trivial permutation, the empty permutation. Okay, so I have a differential equation, so I solve it. So how do I solve it? I go minus p prime over p squared equals minus 1. Why did I do this? Because I know, I mean, this is what you do to differential equations. This is the derivative of minus 1 over p, right? Sorry, 1 over p. The derivative of 1 over p is minus 1 over p squared times p prime. This is the chain rule. Equals minus 1. Okay. That means that, okay, well, if the derivative is constant, that means that 1 over p is equal to minus z plus a constant. Right? Which means that p of z is 1 over constant minus z. But I have my initial value that p of 0 is equal to 1. And here p of 0 is equal to 1 over c. So therefore c should equal 1. So this gives me that c is equal to 1. And therefore p of z is equal to 1 over 1 minus z. Okay? So this is, I mean, this is not the easiest proof that there's n factorial permutations of a set of n elements, but it is one proof. Right? So I told you, I mean, this was kind of a toy example so that we could kind of do a sanity check that we understand what's going on. We got an old thing that's it's like one of the most basic facts in combinatorics. But now I want to apply this idea to a more interesting problem, which is the problem of alternating permutations. Okay. So an alternating permutation is one such that W1 is smaller than W2, which is bigger than W3, which is smaller than W4, etc. until smaller than Wn minus 1, bigger than Wn. What can you tell me about n? This is only going to work if n is odd, right? Because the bigger than come at odd positions. Bigger than W3, bigger than W5, etc. So this is only possible if n is odd. Okay. So let E2m plus 1 be the number of alternating permutations of 2m plus 1. And let's try to apply the same trick. Okay? So let's say that 2m plus 1 is 9. So let's take an alternating permutation of size 10. Okay. I'm doing the derivative, which means that I don't want to do something of size 9, I want to do something of size... Wait, what am I trying to say here?
You want n to go up by 1, not the size of the Like you could look
I
at
mean,
ele- you could
there's
look
two
at
ways of
11
doing this,
instead
which is
of 9.
to separate even or odd, or I could also just allow even permutations, which are the ones that go, bigger, smaller, bigger, smaller, bigger, smaller. So, so what I want to do is this. I want to say, okay, well, let's take an alternating permutation of size 10. Bigger, smaller, bigger, smaller, bigger, smaller, bigger, smaller, bigger. Okay? And let's do the same trick. We're saying, well, if I want this to live on 9, then let me just get rid of the 10. And I get this. And I get this.
Or what did you
Did I miss the 4? Oh, yeah. Thanks.
No one.
No one.
Oh.
Yeah.
Okay. So then, right. I'm realizing my argument is a little bit off, but not too much off. So we're gonna fix it. So the point is that what do I get here? Well, again, I get my set of size 9 is split into 2 parts, and each part is an alternating permutation. Right? So we're going down, up, down, up, down. Then, because this is the biggest number in the set, that means that I do start with down, up, down. So this is an alternating permutation, and this one also. Okay. And so what I get here is something in alternating permutation, star alternating permutation. Okay. Yep.
So do you always have to end going down, or is this as long as you want it up, down, up, down, up, down?
We're gonna go up, down, up, down, up, down.
So it doesn't matter, you have to end down.
That's right. So now, the claim is that this works always, except when when doesn't this work? It doesn't work when. I just want to say it doesn't work in the trivial case when n is equal to 0, and so you just get a singleton here.
Wait, Fernando was asking, we always have to end on a down? Going down?
I was saying that we have to start going on an up.
But we always do because we're taking away the biggest number. So the first one, the next one is down and then up. Because you're taking
Yeah.
away the largest number 10,
Yeah,
you're
yeah.
guaranteed that this will happen.
Yeah, that's right. So after the biggest number, you know that this is going down and then it goes up.
Yeah, that's fine. I was just worried about the very end of the opera.
I'm worried also. But I mean, I'm having a parity issue here. Okay? Which we're gonna have to fix. Okay, let's. What do I get here? I get that the derivative of this is equal to this times this. And the thing is that this works always except for the empty permutation. I mean, you can see that when you take the derivative, you're going to get a constant of 1 here, but you don't get it on this side. You're off by 1. And the initial value, again, is the number of alternating permutations of size 0, which is 0. And so I get a differential equation. Does anybody remember the solution to this differential equation? This is a substitution that is related to this x squared plus 1 in differential equations. Substitute inverse tangent or something like this. Yeah. This is exactly tangent.
Yeah.
The derivative of tangent is secant squared. Tangent squared plus 1 is secant squared.
Yeah.
These are all facts. So I'm having a bit of an issue with the parity that I think I'm just getting wrong in front of you guys, but this is true. This equation is true. This is the solution. Okay. And so what does that mean? That means that, okay, well, this is one of the oldest functions that you've seen in, you learned this function in high school. This function has a power series expansion, which I don't know if you've ever seen it. It looks like this. It's one of the oldest power series in the book. And well, I told you that whenever combinatorialists see a positive integer, we like to know what it counts. So we see these positive integers 1, 2, 16, and we want to know what they count, and they count exactly alternating permutations. And the reason that I know that I'm not worried about the even odd thing is that I chose to present the odd ones separately, but this also works for the even ones. And if you look at the generating function for the even ones, you get secant. In other words, let me just write the whole series. Secant plus tangent. 1 plus z plus z squared over 2 factorial plus 2z cubed over 3 factorial plus 5x to the 4th over 4 factorial. So this is the sum of e to the en zn over factorial, where this one is the number of alternating permutations. Of n. Okay. And the proof is something slightly more careful than what I did. But it's basically the proof, that's it. Question?
No, you just started writing X's.
Oh. Thank you. Okay. And okay, it's secant plus tangent, but really, secant is even, tangent is odd. So if you look at secant, it gives you the even numbers, and if you look at tangent, it gives you the odd numbers. So here's something that you can think about is, okay, well, what if we wanted to do combinatorial trigonometry? What does that mean? combinatorial trigonometry, you could say, definition. Tangent is the generating function for odd alternating permutations, and secant is the generating function for even alternating permutations. Those are the definitions according to a combinatorialist. And then you say, okay, well, this trigonometry is still true. So what should these things satisfy? For example, they should satisfy sine squared plus cosine squared is equal to 1, which, in terms of these guys, is that secant squared of z equals tangent squared of z equals 1. This is an identity that you learn in high school. How does a combinatorialist prove this identity? A combinatorialist says, actually, this just enumerates pairs of even alternating permutations and pairs of odd alternating permutations. And so, this is the same thing as saying that the sum, let's see, what do I want? 2n, 2k, e2k, e2n minus 2k. This is the coefficient of z to the 2n here. Is equal to the sum 2n, 2k plus 1, e2k plus 1. That's the combinatorial formulation of this identity. And this is a perfectly fine combinatorial identity that you could try to prove. And actually, you can prove it. It's possible. And then you will have a combinatorial proof of this identity. And then you could kind of take it further. Okay, what other identities do we know? For example, we know that tangent of x plus y is equal to tangent of x plus tangent of y over 1 minus tangent of x tangent of y. So, again, you can think of this as being a statement, a combinatorial statement about alternating permutations, and you can prove it in that way. So, I don't know, I mean, it's not maybe the best way to do trigonometry, but it's kind of a fun way to do it.
How about sine and cosine? What do they show?
Sine and cosine have extremely boring power series, right? So the question is, okay, what do sine and cosine count? And sum, what is it? Minus 1 to the 2n plus 1. Or no, maybe
You just figure one to the end.
to the end, right? So, counts this, I don't know. I mean, for one thing, it doesn't have positive coefficients, so then we get a little bit less excited, but also the coefficients are just 1s and minus 1s. But it is true, secant is 1 over cosine.
Yeah.
Right?
Yeah.
Okay, so then that means that secant of z times cosine of z is 1. And this is a combinatorial identity of alternating permutations. Right? These are alternating permutations, and these are 1s and minus 1s. So this is going to tell you that some alternating sum of alternating permutations is equal to 0. So I don't know. I mean, I don't know how far anybody has bothered to push this, but it's kind of amusing. Okay, that's it. I said I was going to talk shorter, and I ended up going longer.
So you cursed yourself? Yeah, right.
I always know.
Yeah, on that note,